Just as a reminder, we're going into detail about one of the fundamental principles that we've been talking about since the start. So we just did entropy, and now we're doing enthalpy. So chemical energy decrease is favored. So what we have here is we don't actually know what enthalpy is. We just can only measure the differences in enthalpy. So enthalpy is the amount of heat energy or the amount of energy stored inside these chemicals. And we don't know what that is. Chemical, potential energy, strong nuclear force, things we haven't even discovered yet. And so the only thing that we can actually do is measure the amount of energy that is different. And we don't even do that directly. So what we have is we have chemical energy, and it gets transformed into heat energy, and then it gets lost into the environment, which is entropy. So sort of transferred through kinetic energy to other molecules, etc. I'm just using this equation here because you have to memorize this when you do biofuels. So photosynthesis is this direction, and we're just doing respiration, which is going in the opposite direction, which is 7 to 12. So it's entropically favored as well as enthalpically favored. So it's entropy is favored here because it's loss of heat, and enthalpy is favored, loss of heat. Entropy is favored, increase in particles. So life makes no sense, does it, going in that direction? And so I'll probably never talk about that again. So make sure you know that. We're measuring heat energy, so we're measuring a transformation of energy. So we're assuming that heat energy has come from the chemical energy that's been lost. That's all written down here for you to read. I'll leave it for you to read that. Now, I'm going to say enthalpy all the time because I'm lazy, but we're never actually going to be using enthalpy. What we're going to be doing is this, which I'll probably never say ever again: standard enthalpy change of reaction. So this is delta, so this is change, and the theta is the standard conditions. So most syllabuses and textbooks get lazy and just write a degree symbol, and then practically speaking, we get even more lazy and just write delta H. And then we never say standard, it's just assumed, which is this bit. And we never say change either, it's just too many words. Just like I never say decimeters cubed, I just say liters because it's quicker. So I'm going to say enthalpy all the time. And what I'm really meaning is standard enthalpy change of reaction. All right, though I think I am pretty consistent with keeping the proper symbols in all the calculations. Okay, so that's what we're doing. So the standard conditions are standard ambient temperature and pressure, not standard temperature and pressure at 0 degrees Celsius. We're doing 25 degrees Celsius. And the pressure's 10,000 kilopascals, 10,000 pascals, so 100 kilopascals. That used to be 1 atmosphere, which was 101.3, but they've gone metric on everything. You will need, as we've done gases now, so you might be aware of that. If they're in solutions, it's 1 mole per litre. Okay, so we're done and dusted with that. So make sure if you're getting specific questions on the exam, you do all the proper things, even though we're going to be saying enthalpy quite a lot. So the delta H being favoured is negative, which means this one is larger than this one. And so the energy released when it's formed is quite large. Also, if the energy to break that will be quite large as well. So that's the bond enthalpies we'll cover in another lesson. And so there didn't take much energy to break this. To break it, putting energy in. It wouldn't take much energy to form it either, and so energy would get released on forming. And so what we're doing is the bonds broken minus the bonds released. And so that one's the larger one minus the smaller one. So there we go, bonds release more energy when forming than they take to break. That also makes these more stable. They contain less stored energy, and so they release a lot of energy to break. They also, to form, they'll also take a lot of energy to break as well. Okay, And so we'll move on from there.